In this video, we're going to develop a first-order heat transfer equation for an enclosed space. Enclosed space might be, for example, your house, or a greenhouse, or a small enclosure that you're using to test an experiment in lab. If you think of your house, in general, you want to keep your house at a nice warm temperature or comfortable temperature inside, but the temperature outside changes. It goes cold in the winter or hot in the summer. And heat either enters or escapes through the windows or through the walls or through the doors and so forth. And what we want to do is we want to develop a model, a simplified model for this house so that we can figure out what the dynamics of the house are. We can figure out how long does it take to warm up the house when we turn on our heater. We can figure out how much energy do we need in the dead of winter to keep the house at a reasonable temperature. We can figure out how long will it take for the house to cool off, for example, if we turn down the heat when we go to bed at night. We can do all this with some simplified equations, some approximations, but in general, even though the house is obviously a fairly complex structure with lots of different pieces to it, in general, this approach works pretty darn well for designing houses, for designing heating systems for houses, for example. So let's say that we have a house, and the house has windows and doors and roofs and walls, and I'm not gonna draw all those because I don't want to clutter this up too much. And the first thing we're going to do is we're going to draw a control volume around this house, and we're going to say that everything inside of this house is the same. Even though the walls are more massive than the air, we're going to lump everything together and say that inside the house the temperature everywhere is the same, and we're going to say that because of this, there's a certain amount of energy inside the house, where energy is proportional to the temperature, and I'm going to put a little subscript here in for inside, times some heat capacitance. Now again, the walls have more heat capacitance than the air, but if we add up the heat capacitance of the walls and the temperature of the walls and add that to the heat capacitance of the air and the temperature of the air, etc., 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 again, we can lump all this together as into one energy term. Now, how does energy get in and out of this control volume? Well, there's two ways. One is energy can come in through the boundary in the form of heat, and we'll call that QBND, for heat. Q stands for heat, traveling through the boundary. And the other way is that we can have, for example, a furnace on the inside of the house, and it generates a certain amount of heat, and we're going to call that QI for interior. So we have heat being generated inside the house by the heater, by people, by pets, when you're cooking, all that sort of thing. And we have heat that's coming in through the house walls by convection or conduction. Convection meaning air leaking through the windows, or conduction meaning heat coming through the walls. Radiation, if you've ever seen an infrared photograph of a house, you can see the different parts of the house have different amounts of radiation that escape through the house. When we do this, we can write an energy balance for the house, and we can say that the change in energy over time is equal to the heat that comes across the boundary plus the heat that is being generated internally. These are just energy flows, and the amount of energy that comes in per unit time is how much the energy in the interior changes. But since we said that E equals some constant c times T in, we can write on the left-hand side c times the derivative of T in over dt equals Q boundary plus Q interior. Now Q interior